And now we are privileged again to have another amazing speaker. In fact, Yuval, Yarom, was one of the authors of Spectre and Meltdown in terms of the research, and the only Australian of that list. And he's going to talk today about speculative execution being considered harmful. And it's such a low-key topic, speculative execution considered harmful, but it has such significant impact. So let's all welcome Yuval, and we'll go from there.
Thank you for the introduction, and it is a pleasure to be here. Thanks everyone for coming. This was not, I was not the only one to do this work. There are a lot of co-authors or collaborators. In fact, we were 5 different research groups that have found parts of these vulnerabilities, each of them independently, and I'll just introduce them. Jan Horn from Google is probably the smartest of us all. He found both vulnerabilities. He was the first one to identify them, the first one to exploit them, and the first one to report those to Intel. Another group, Daniel Gruss, Moritz Lips, Stefan Mangard, and Michael Schwartz from the Graz Technical University, they discovered Meltdown. They are probably the strongest research team on the area of microarchitectural attack that we currently have in the world. Werner Haas, Thomas Prescher are both ex-Intel, work at the security company Cyberos in Germany. Anders Fogh is a private researcher. He does research, just does hacking, publishes his results, work a lot in the area of microarchitectural attacks. And our group was Mike Hamburg, Daniel Genkin, Paul Kocher, and myself. For those who don't know, the name Paul Kocher is the person that first published any results on side channel attacks. So he's the first person to take a scope and put it to a computer while the computer runs cryptography, decryption in that case. Mike Hamburg, from our perspective, is the one that came up with the question. And Daniel Genkin is a brilliant young researcher. He's the person that decided to check what sounds computers make while they decrypt data, managed to show that acoustic cryptanalysis works. And one of the questions that we are always asked is how come no one found these problems for the last decade or so, and suddenly 5 different groups find it. And there are a lot of conspiracy theories running on Twitter. If you look, Intel always knew about it, that's the NSA, and we did not really discover it, and that the problem doesn't really exist. The answer is much simpler than that. We were all working in side channel attacks. This was the natural extension of the last 4 years of work for most of us. And we were just lucky that Jan Horn gave Intel 6 months to disclose everything, otherwise he would have been the only name here. Okay, so what are we talking about? Basically, we have 2 different attacks. One of them is Spectre, which it exploits a design flaw in most modern processors. I'll explain more about how the attack works later. What we do is that we look at speculative execution when the processor runs code speculatively, assuming believing that the program will go there, and that leaves traces, and we exploit these traces. And Meltdown, which is more specific, it is a bug, although Intel doesn't acknowledge, it is a bug in Intel implementation of memory protection. It exists also in some ARM processors, and the result is that even though memory is protected from reading, we can indirectly read the data from there. From the attacker perspective, Meltdown is more potent. It's extremely easy to exploit it. We can read the whole memory of the processor or the computer. Anything that is there, we can find out. From Spectre is a little bit more complex to exploit. But it will probably remain, it is probably much harder to fix and will remain for longer with us. And it allows us to read data from other processes. It allows us to bypass language-based security, so the protection that it provides. Okay, the main thing that we use is microarchitectural channels. What these are, basically, when we have a program and it executes, it leaves some traces in the processor states. And these footprints that it leaves, it's just a product of the fact that the processor tries to optimize the performance and guess what the program is going to do, and that's information that stays there. And as the program continues to execute, it leaves more footprints, and we have known for probably 15 years now that if we analyze these traces, we can learn information on what's happening there. And this gives us information, so we have a program running, it sends us information. The technical name for this is a channel, an information channel or communication channel. And when we analyze those, when we work with those, we distinguish between two types of channel. The covert channels are intentional. We have a sender that affects the processor state and the receiver that reads the processor state. And we have a side channel that is inadvertent. We have a sender that doesn't want to send, but does it by the way it works, and the receiver receives the data. And for many years, covert channels were interesting for military people that wanted to run multiple security levels on the same computer, but no one else was really interested in those. Side channels were more interesting because we can use them to find cryptographic keys, we can use them to break ASLR, we can use them to get keystroke information, everything that we want, we can use side channel. So most of the focus was on side channels. Spectre and Meltdown, in my opinion, changed this because we really use covert channels here. Before we go to those, just an example of what are these channels, how do they work? And the channel that we will use is a cache channel, and what it exploits is a difference of speed between the memory and the processor. And what happens is that over years processors have become really fast, and memory has become faster, but not at the same rate. So when the processor reads data, it has to wait for this data to come to the processor. And if the processor needs that data again, it would have to wait for it again. So to fix this, these processor designers put a small bank of memory called the cache between the processor and the memory. And the cache, because it is smaller and because it is different technology, it is much faster. And now what we can do is when the processor reads the data, a copy is left in the cache. And the next time the processor needs that data, it can get it much faster. But the fact that this data is in the cache is some trace or a footprint of what happened earlier. If we can find what data is in the cache, we know what different other programs have accessed before we access that data. And this is what we exploited for the past 4 years. We exploited caches, we exploited the bus contention, we exploited every aspect of the processor, almost all of them, and designed attacks from those. Now, the other aspect is speculative execution. And for speculative execution, we need to understand a bit more about how processors work. So, if we look at our processor, we have a machine code, something that runs, a program that runs, and when we think of that, we think of it as executing the instructions one by one and processing them one by one. When one completes, the next one starts, and so forth. And this is the way that we think about processors because that's the way that it's easy to analyze or understand what's going on there. However, each instruction that itself consists of multiple steps. In modern processors, we have 30 to 40 steps. We'll look at 5 here. So in this example, I have 5 steps. First, we need to fetch the instruction from memory. Then we need to understand what the instruction is, get the arguments that it processes, do whatever it does, add the arguments, multiply, whatever we want. and then write the data back, and by this time the instruction completes. And if we look at that, this takes 5 cycles to execute an instruction. And that's not efficient. On the other hand, we know that if you look at those, each instruction uses different unit. The unit that fetches instruction from memory is different from the unit that does the calculation or computation. So we can use them in parallel. And that's pipelining is the solution that does that. And basically what we do is we execute multiple instructions in parallel. So we first fetch the first instruction, and then in the next cycle, we decode the first instruction and fetch the second one, and then we proceed to get the arguments for the first, decode the second, fetch the third, and continue that way until the first instruction completes, the second, and so forth. So basically what we have sort of a diagonal front on the execution of the program, and as it progresses, the program executes. And this allows us to complete 1 instruction per cycle on average. So we have 5 instructions running in parallel, 5 stages for each. On average, we get 1 instruction per cycle. But this creates some problem. For example, we have problems with dependencies between instructions. If, for example, the first instruction does a division, and this next instruction takes the result of this division and needs to calculate on it, then we can't start executing the second instruction before we completed the first one. So what the processor does in that case is what we call out-of-order execution. It actually executes the instructions whenever the data is available, rather than just executing them by the order that the program executes them. So in this example, we'll fetch the instruction, do the execution, and now the second instruction needs to wait for the results of the first one, so we block it, but everything else continues, finish the first instruction, and then we can continue moving forward. Now, the important thing that happens is that at this stage, we got the third instruction to complete before the second one. So the processor, instead of really completing it and storing the data, store this information in a temporary buffer, and it will actually, the instruction will wait until the previous instruction completed, and then all of them complete together. So what we have, again, is we have our front that is going, we don't know, multiple instructions that run at different stages, and behind that, we have what completed execution. And now we have a question, why did the processor not finish the execution of the third instruction before the second one? And the answer to that is that it would create a problem. We were at this stage. Now what happens if B is 0? If B is 0, the first instruction should fail. That means that neither the second nor the third should execute. So basically, we have to wait with all instructions until all preceding instructions finished before we can accept the results. And what the processor does in this case is, what that means first is that all out-of-order execution is speculative in nature. We start executing instruction before we really know that they will be needed. And to solve the problem of speculative execution, what the processor does is when it reaches to this stage, finds out that B is 0, the divide should fail, it just abandons these instructions, throws the temporary results that it may have calculated, and continues working, and continues handling the exception. So the behavior is as if the instructions were executed one by one sequentially, but we got the performance benefit of using of pipelining. Now, this mechanism is also used for handling branches. The problem with branches is that we don't really know. The processor starts executing, it reaches the point, it starts executing, it reaches the branch instruction. And this branch instruction may depend on data that has not been calculated yet, because the front hasn't, or the green area hasn't reached there yet. So what does the processor do? The processor asks a fortune teller what the branch will do. And we have the fortune teller, they look at their crystal ball, and we have, it tells us the branch will go to the left, sorry. Depends on which side I look at that. So the processor continues executing, and at some stage, it will reach to the branch with the data and will know what the result is. So now we can test whether the prediction was correct. And if it was correct, everything is well, and we can continue executing. If it wasn't correct, what happens, what it does is it goes to continuous execution from the other branch, other side of the branch, and abandoning everything that has been calculated on the way. And the nice thing about this mechanism is that we can't decide which way the branch will go before we have the data. So with speculative execution, if we did a correct prediction, we gain performance benefits. If we had a misprediction, then at the worst case, we just didn't get any performance benefits. We just execute as if we just didn't do the prediction. So we lost a bit of power for calculation, but performance remains high. Technically, we have two different branch prediction mechanisms. Well, we have more, but two important ones. One of them uses the branch history. It checks on conditional branches whether they were taken or not, and we have a fortune teller that tells us whether the next access to this branch will be taken or not. And then we have the branch target buffer, which is used for indirect branches. So if we have a branch based on a register, or even a return instruction, which goes to somewhere which the program doesn't know a priori where it will go. And this is a different predictor that just tells us from here the program will continue at a different location. So this is the background. We have speculative execution, how it works, and we have cache footprints. So what our discovery? The main discovery with both Spectre and Meltdown is that whenever we have abandoned calculation, what is abandoned is the nominal results of the calculation. What is not abandoned is the footprint this calculation left in the processor. So the Spectre and Meltdown are techniques that use are techniques for extracting these footprints and finding out data on what's going on in the computer. And the distinguishing feature between them, Meltdown exploits instructions that should have faulted, or that fail, but something execute after them, and Spectre exploits the branch prediction. The attacks basically work on an attacker that runs on unprivileged code, where unprivileged could be a user process trying to access kernel, or one process trying to access another process, or JavaScript code trying to access the data that is in the browser. And what the attacker does, it finds a piece of code that we call a gadget, that the attacker can control the input to that gadget, and the gadget sends information over a channel. And so what the attacker does is cause speculative execution of this gadget with the input that the attacker controls, and then learns what the gadget leaks through a covert channel. How does this work in practice? First, we'll look at Meltdown. So the typical code for Meltdown is 2 lines. Usually we write it in machine code, but it will be easier to see it in C. The first one dereferences a pointer, and the second one takes the value of read from that pointer, multiplied by 256, and dereferences an array with that index. And the gadget here is the second line. And now we'll look at how this works. So we have our program, our address space of the process, And before Meltdown, the address space was divided into two parts. The left part is the user space, so where all the data that the user process can access. The right side is the kernel address space, which is protected. So it is mapped to the same address space, but the user cannot access it. Only code running in high privilege mode, only code running within the kernel or within the operating system can access that location. And now we look at having a cache in the system, and we start with beautiful, beautiful. So we'll start with a pointer that points somewhere in memory. Both of these locations are cached, and we have the array that is not mapped, that is not cached at the moment. And let's look at what the execution looks like. The first thing we do is we dereference a pointer and get some value from memory. And then we use this to point to somewhere inside the array and access this data, and that means that this data comes to the cache. This is the way that this code works, no problem in here, right? Beautiful. So now we'll go to a different scenario. In the different scenario, the pointer points to a location in the address space of the kernel. So it's a location that the user should not be able to read. The data from this on this location happens to be cached. And now what we do is we do the same thing. We dereference the pointer. At this stage, what the processor does is two things. First, it accesses the data, and in parallel with that, it checks whether the user can access this data. And it will take it some time to find out that the user is not allowed to read this data. While the user is not allowed, we speculatively execute the next instruction. The next instruction is use the data that we got from that memory to address a location inside our array and get that into Y. Now, this will happen, and at some stage the processor will realize that it has made a mistake, it shouldn't have allowed this access, it will abandon, the value of I will not change, the value of Y will not change, and we'll get a trap. And here comes a Meltdown attack. We have the Meltdown Attacker. Now the Meltdown Attacker does a very simple thing. It tries to read one location from the array and measure how long it takes for the data to come to the read, how long it takes to do this read. And in this case, this data was not cached, so the read was slow. And then it tries another location, and again, it will be slow. Only when it tries a location that we have already brought to the cache earlier, this read will be fast. And when the read is fast, we know what the index that we accessed the array in, and therefore we can find out the value of I. And this value of I comes from the kernel space, so we can read data from the kernel. This is basic Meltdown attack. There are some complications in it if you want to actually implement it. First thing, you need to handle the fact that the process has already died. And so you need to have some mechanism that doesn't kill your process. There are several ways of doing that. One is to catch interrupts. We can do that in Unix, or at least in Unix you can do it easily. And the other way is to use, Intel has a beautiful feature called the transactional memory, TSX. And what TSX does is that it tries to execute some instructions, and if it fails, restores the status and goes back. And the beautiful thing about it is that if it gets an interrupt while executing, it just goes back and says, oh, well, oops, I couldn't execute this transaction. So we start a transaction, do this code, it fails, and we know that we can continue running. The other thing is that Intel has some mechanism, which we don't know why they do it, that at some stage in here, when it finds out that the instruction should be dropped, it also resets the value of I to 0. So in some cases, what we will read from here will be the value of I being 0. And the problem is that we never know whether the 0 that we read is the real value or not. So the solution is try to read it 1,000 times. If one of them is not the 0, you found the value. If all of them are 0, it's probably 0 in there. So this is Meltdown. Now, Spectre. Spectre has 2 variants, one for each branch predictor. So for the first variant, this is a typical code. This code is found either explicitly in C programming or implicitly in programs that check up for array-bound access. And what this code does is very simple. It takes an index to an array, checks that it is within the array bounds. Then if it is, it takes the value that the index points to and accesses a different array, again, with the value times 256. And again, the gadget is here. Now, how the Spectre attack works? The first thing we do is we call this code. We execute it with an x, with a legal value of x within the array. And again, let's look at our memory. We have all the elements in memory, and we also have some secret data that we want to read. And the first thing we do is compare the value of x with the length of the array. If it is smaller than the length of the array, we read the value from the array. This is used as a pointer to the second array, and we can everything works nicely. When we do that with a value within the range, within the array, our branch predictor learns that the value that we used is within the array. And she knows that the branch was not taken. We have not skipped the code of the gadget. Okay. So now, let's look at the same thing with a cache. We have the secret cached, we have X cached, and the rest is not. And we have our attacker calls now with a value that is large, much larger than the array. At this stage, what will happen, we'll start executing testing the condition, but because array len is not cached, it will take some time for this if statement to execute. While we bring this data from the cache, we need to know whether, the processor wants to know whether to continue inside the branch or to go outside, consults with our fortune teller, it tells it that the branch is not taken, so it starts executing. Takes the value that x points to, and because x is large, we now get a value from the secret, and the rest continues the same way as before. We get the value into the cache. At some stage, the array length arrives to the cache and arrives to the processor, and the processor realizes that it was wrong, it was a misprediction, take everything back, but we still have our trace in the cache, and we exploit it the same way. The beautiful thing with this attack is that we can do it from JavaScript. We just do the same or similar code in JavaScript, test for array length, and we can use it to read everything within the browser. It only works for browsers before they were fixed. Now it's a bit harder to do the same attack. The second variant of Spectre is a bit different. It uses the branch target buffer. So in this scenario, we have the attacker that runs Spectre, and we have a victim that runs runs whatever program it runs. And these are protected from one another. We are not expected, the attacker is not expected to be able to read anything from the victim. And now we look at their address space, and we have the address space of both of them. The attacker has its own address space, the victim has its own address space. Because we use virtual addresses, these could be the same addresses in both sides. And in the victim, we have some indirect branch that, in this case, it takes a value of a register and branches to the location of the register. And we have some gadget that contains code that basically does read I from memory and multiply I by 256, find where it is in memory. The important thing is that we don't really need the branch to ever be able to jump to this gadget. This could be totally different pieces of code. What we will exploit is that we teach the branch predictor to branch to the how many bugs are in this code? Currently, I just found one, at least. Anyway, we teach the branch predictor that this branch is supposed to go to that gadget and then execute it. So how do we do it? We take the address of the gadget. In the attacker, what it does in its own address space, in the same virtual address as the attacker, as the jump instruction at the victim, we take the value of the gadget and we do an indirect jump. And in the location of the gadget, we just do a return or whatever way of recovering and being able to execute that. And then we execute this piece of code. So the attacker just run a branch into its own address, and it does it several times. And after it does it enough times, we get our branch predictor to learn that this is the branch that happens from this location. Once that happens, we can actually execute the attack. We cause the victim to execute this branch. And because we have speculative execution, we have the branch target buffer will tell, or the branch predictor will tell the processor that the execution is supposed to continue from that gadget. And from this, it follows the same way that we had the attack before. So these are the two attacks, and now we'll look at the other side, how we prevent or how we protect our systems from these attacks. So first, we have Meltdown. The solution for Meltdown is simple. We use a separate address space for the kernel. So if we look at the process as it was before, we split it into two different address spaces. One of them only contains the user level, and that's where the process runs. And the other contains the kernel map and a copy of the mapping of the user, because the kernel wants to access this data easily. The main problem that was initially seen with this is that we have an overhead when crossing address spaces. So whenever you do a system call, we need to move from user level to kernel to system level, and that takes now longer because we need to switch address spaces. Performance results that were published range from almost no performance impact to 30% performance hit, depending on the workload. Another problem with this solution is that it's not easy to implement it. So not a long time ago, Microsoft had to issue an emergency patch because it turned out that it solved Meltdown by giving user full access to the kernel space. And the more important issue is that this does not really address the core issue here. The problem that we have with Meltdown is that page table protection, the protection that the processor provides, doesn't really work. What we have, the solution here that moves the parts of the address space or the kernel address to a different address space, it solves the symptoms. It's like giving Panadol to person to avoid the pains caused by a tumor. It solves the symptoms, but the problem remains. And any system that uses or that relies on page level protection or on the processor provided protection will fail to work. Second mechanism suggested for variant 2, the solution is to adds some processor features that prevent prediction across security domains. Basically, what that means is that instead of one branch predictor, we have two. Whatever we teach the first one, we don't teach the other one doesn't learn, and vice versa. On a technical level, we have three layers of protection. The first one for processors that have hyperthreading, Intel hyperthreading, they prevent learning across hyperthreads. So whatever happens in one hyperthread does not affect the other hyperthread on the same core. The second is that code running in higher security level does not learn from code running in lower security level. So whatever the user space teaches the branch predictor does not affect the kernel when the user switches to the kernel. And to protect between across context switch, so we run one program before another and they are in the same protection level, there is another way, another instruction that just kills the branch predictor. So whatever was in the branch predictor is deleted, and now we don't rely on that. Technically, this should solve all issues. Practically, when Intel issued the first patch for that, it caused some machine to stop working. Microsoft, in this example, just disabled the fix. Others did similar things. I think it was 2-3 weeks ago that Intel released the new patch, and they also told us that they are not going to patch every processor because they don't know how to do that. AMD was much more careful, and the patch has come out, I think it was yesterday. So until now, AMD processors were vulnerable, and now we will learn whether AMD is doing a better job than Intel. Last variant, Spectre variant 1. The solution, the most commonly suggested solution is compiler patches to block speculative execution. The idea is that if we have our footprints here, we don't let the code execute beyond the point that it starts leaving footprints. So when we get to this position in the speculative execution stops, and then if we learn that we went the wrong way, then no footprints, we cannot exploit this. Theoretically, this works. It's very easy to do that. We just need to put in, Intel has instructions that stop speculative execution. We put them on both sides of any conditional branch, and we are protected. The problem with that is that these branches are expensive. In tests that we have done, SHA-256, when we start adding all these branches into it, all these barriers into it, executes about 60% slower, which is usually not acceptable. So instead of using that, the suggested solution is let's use static analysis. Our compilers will look at our code and decide whether this code may leak information or not, and put the barrier if they see something that may leak information. Microsoft has done that. There is a patch in MSVC. There are other patches for LLVM, so we have some patches around. And we tested one of them, or Paul Kocher did. And the result is that, yes, it does block some patterns that leak information, exactly those that we mentioned in our paper. Paul tried 15 patterns. 2 of them were blocked, the other 13 were not. And the problem is that it is not really easy to analyze the code and see whether it leaks or not. And they're going to try, and it will probably be better, but the problem is will still be there. No, we're still there. Another solution that is suggested is limit the memory access or use of data. And the example that, one example for that is to replace this piece of code that we've seen earlier with something along these lines. So what we have, instead of testing that we are within bounds, we force the value to be within bounds. We just reduce it modulo the size of the array that ensures that everything is inside, and we cannot read things outside the array. And we can do it with or without the array, the bound tests. And technically it works. But it only works for the scenario of arrays. It only works, again, on the sort of attacks that we have shown. It does not address the core problem that speculative execution may leak information in other scenarios when we don't test for array length. So we are left with a problem that we don't really have a good solution. And in a sense, this mirrors what some of us may remember from the 80s, 90s, that the scenario that we had with buffer overflows. When they started appearing, people suggested solutions that are still used today. Non-executable stacks block the attacks that were popular in the early 80s. But as long as we don't address the core problem, the problem still remains. So we believe that Spectre is going to haunt us for many years, even though Intel promises the next generation of processors will solve it. So, to sum up, for the past decades, processor development focused on performance. There was some work on security, but not enough. We got the result with Spectre and Meltdown. Hopefully, these are the last ones. This is not much different from what happens in software development. Time to market trumps security every time. Performance always more important. But so we have bugs in software, but the problem here is that it's much harder to fix those. It's very difficult to fix a processor once it's out in the market. Second thing is that we are going to live with this problem, so if anyone is interested to look at it more, that's something that I think will be a very good area to investigate for at least 2-3 years, 2-3 coming years. And the third thing is that microarchitectural channels, particularly covert channels, now matter. And being able to eliminate them or to understand them and know what's happening there is much more important than we thought it was until a few months ago. And in that respect, I would like to recommend everyone go to Qian's talk today, because she's going to speak about how we block or how we don't block these channels. And with that, I will conclude, and I'll be happy to take questions.